In question 9, this is the only question on this exam that really explicitly deals with higher order, so higher than second order material. We've actually got a sixth order differential equation. We're told the sixth derivative of y minus 5 times the fifth derivative plus 4 times the fourth derivative minus 20 times the third derivative equals 0, and we just want to solve this equation. That's a linear differential equation, that's homogeneous, and it's got constant coefficients. So much like 7a, we're really just using the method of the characteristic equation. It's just in this case we've got a little bit more work to do because of the fact that this is going to be a sixth degree polynomial rather than just a nice little quadratic. But the principle doesn't change. So the characteristic equation in this case, and again, like I said in the video for question 7, you could do this from first principles and actually formally assume that y is e to the rt, work out all the, in this case, all the 6 derivatives. But really, we know from class how this is going to turn out. The sixth derivative is going to wind up as r to the sixth. The fifth derivative will wind up as r to the fifth. The fourth derivative will wind up as r to the fourth. And the third derivative will wind up as r cubed. So our characteristic equation then is r to the sixth minus 5 times r to the fifth plus 4 times r to the fourth minus 20 times r cubed equals 0. That's not quite as bad to factor as it might initially seem, because of the fact that we don't have a quadratic term or a linear term or a constant term, so we can immediately factor out an r cubed, leaving us with r cubed outside of r cubed minus 5r squared plus 4r minus 20. And even being left with a cubic to factor there, that could require the rational roots theorem and synthetic division, but in this case that one can actually be done by grouping. Because in the first two terms I've got a common factor of r squared, so I can write that as r squared times r minus 5, and in the last two terms I've got a common factor of 4. So leaving me with a plus 4 times r minus 5. And so therefore, if I factor out the r minus 5, I've got r cubed times r minus 5 times r squared plus 4 equals 0. And I've now factored that equation as much as I possibly can. So this tells me that my roots are r equals 0, and that's a triple root. I've got r equals 5. That's a distinct or unique root. And I've got r squared plus 4 equals 0, which means r squared would be minus 4. So r is going to be plus or minus the square root of minus 4, which is plus or minus the square root of 4, which is 2, times the square root of negative 1, which is I. All right, so I get one unique real root, that's 5. I get one repeated real root of multiplicity 3, that's 0, and one unique pair of complex conjugate roots, that's the plus or minus 2i. And that's really all I need to know. Immediately then, I can start composing the general solution. So if I take them in the order that I found them, what 0 will do is it will generate one solution of the form e to the 0t, which is really just 1, one solution of the form t times e to the 0t, which is just t, and one solution of the form t squared times e to the 0t, which is just t squared. So I'm going to get 3 terms in my general solution, c1 times 1, or just c1, plus c2 times t, plus c3 times t squared. My distinct real root, 5, is just going to give me one solution of the form e to the rt, so in this case e to the 5t. So my fourth term will be a constant c4 times e to the 5t. And then my unique complex conjugate roots work just like they would if this were a second order equation. In fact, just like the homogeneous equation with constant coefficients we solved in 7a. So we're going to guess, because this is pure imaginary. There's no exponential factor here to account for. So we're just going to guess. Well, cosine of 2t would be a solution. So C5 times cosine of 2t goes into the general solution. And sine of 2t would be the other solution. So we'll get C6 times the sine of 2t. Sixth order differential equation should have 6 distinct terms in its general solution. And that's certainly what we've accomplished here. So that's all that it takes to solve that 6th order ODE.